I wanted to kind of remind you at the start of this conversation, we promised to mess with your brain. So carbon credits, right? Incremental change, so. We looked at the other part, which is don't rub dead jellyfish on your face for cosmetics, which was probably a good thing. So the other part about this is, as we thank Arvind and Poe for this kind of blunt insight also, one of the things that we ended up, the last conversation was, how do you make step changes? The other part was the comment about moving atoms around as opposed to electrons or software. When it gets into the fundamentals of science and how to move things around, can I have the clicker? One of the best people that I have had the pleasure to know is my dear friend, Professor Thomas Jaramillo from Stanford. In a short space of knowing the professor, he has also wreaked havoc with my brain, and in a very short space of time. And one of the things I've really admired about his research is about the fundamentals of the work he's doing and how the work he's doing enables the step changes in a lot of the things that we think we're going to take for granted. And with that, I'd like to invite the professor up.
No problem. Feliz Cinco de Mayo, everybody. Good afternoon. It's wonderful to be here. I want to thank Manu and the organizing team for the invitation to be with you here today. That was a really great panel. I'm going to switch gears a little bit, but connect to everything that they just said. The long and the short of it is, I love renewable electricity. I love batteries. I love a lot of the new tech that is starting to disrupt our world. The energy transition is here. It is happening. We need it to be affordable. We need it to be reliable. We need it to be low carbon. The challenge is, that is not enough. Batteries and windmills and solar cells alone are not going to solve the problem. They're a big part of the solution. But we need a lot more, and where we are at Stanford University, at SLAC National Accelerator Lab, what we're trying to do is innovate in that space, really create the foundations for new types of technologies that will completely change the way that we do things for the better. Again, we want energy that is affordable, reliable, and low carbon. So a little bit about myself. I'm rostered on 3 different faculties right now, which gives me a lot of room to maneuver in the Stanford ecosystem. I'm part of the Department of Chemical Engineering, which is in the School of Engineering. I'm part of the new Stanford Door School of Sustainability as part of the Energy Science Engineering Department there, and I'm part of Photon Science at the National Lab at SLAC. And when you look at these 3 different entities, that becomes a tremendous playground with which we can innovate in spaces that are really important to the future of sustainability. So as I'm a faculty member, I'm going to start today really with a question. What are you breathing right now? I ask you to think about the molecules, the elements of the periodic table that are going into and out of your lungs at this very second. How many of those can you name? Raise your hand. How many molecules or atoms or types of elements are you breathing right now? How many could you count? 3? Maybe 4 or 5. Well, let me show you what we're breathing. We're breathing actually quite a bit, and that's really where I want to start. Many of you said nitrogen. That's 78% of what we're breathing, of course, 21% oxygen. Pretty important for us to live. Did you know you're breathing 1% argon? You probably knew you were breathing 400 parts per million in climbing of CO2. You're probably breathing about 0.5% of water, and a whole host of other elements, neon, helium, methane, etc. So there's a lot of molecules out here. The atmosphere contains 10 to the 19th kilograms of stuff. And the question that I would posit is, how can we make use of that and renewables to make the chemicals and fuels that we need? Because batteries and electricity are not enough. We cannot eat electrons. We cannot be inside this building made of electrons. We cannot fly on a vehicle that is made of electrons or that runs on electrons if we're going to go from here to Frankfurt. So how do we solve that? And that's really the nature of what I want to talk about today. Now, nitrogen's an interesting one. Arvind was mentioning a moment ago about the amino acids and how important those are to live. Absolutely. We have fixed nitrogen all over our body. Our DNA is composed of amino acids. Our proteins, amino acids. Our enzymes, amino acids. We need fixed nitrogen to live. And even though we're breathing 78% molecular nitrogen, our body cannot do anything with that. It's one of the strongest bonds in nature. And so how did we get here in the first place? Well, that's the natural nitrogen cycle. You might remember from grade school. Lightning strikes, lots of energy. It goes through 78% nitrogen, rips it apart into a fixed form that enters the soil. The plants can then use that and make the amino acids. We can either eat those plants directly or eat the animals that eat those plants. That's how we get the fixed nitrogen into our bodies. Now, what if I snap my finger and then all of a sudden that natural nitrogen cycle no longer works? It no longer exists. How would we survive? I've got an answer for you. Engineers have figured that out. And that's the Haber-Bosch cycle. This is how we feed the globe. 180 billion kilograms a year of production of ammonia, grabbing that 78% nitrogen air and grabbing hydrogen that is coming from almost entirely fossil fuels, ripping out those bonds and putting them back together to go from N2 plus H2 goes to NH3. Now, we know there's about 8 billion people on the planet. We can all do the math. 180 billion kilos a year divided by 8 billion people is over 20 kilograms a year. That's over 50 pounds of ammonia is what we account for every person on Earth. Half the fixed nitrogen in your body, which came from the food that you've been eating at lunch and breakfast and the night before, all that fixed nitrogen, half of that touched one of those iron nanoparticles in some Haber-Bosch facility somewhere around the globe. Ammonia is a really important molecule. Mass-produced, reaches billions of people, and depending on where you live, could be pretty low cost. Here in the United States, maybe 60 cents a kilogram. What could you go to the grocery store and buy for 60 cents a kilogram? It's actually quite remarkable. Scientists and engineers have figured this out, and it's not the only molecule in town. There's a lot of other molecules in town, also at large scales. I'm just showing you a few examples here. We make over 70,000 different molecular products. 70,000. Trillions of kilograms of stuff, materials, chemicals. These are the things that we build buildings with. These are things that we eat. Forms the dyes in clothing, et cetera, et cetera, et cetera. How are we going to make this sustainably? There's no process to do that. Almost all of this comes from fossil resources. So I'm very grateful. I consider this to be one of the greatest human accomplishments of all time, to be able to draw from resources underground and in the air and convert them into the things that we need. The challenge is it's not sustainable. It's not equitable. It reaches some billions, but not all billions equally. And I think this is one of the greatest opportunities for new markets because we don't have solutions for this whatsoever. And so this is the space that our research lab operates in, and I'm going to share with you some of our ideas along these lines. We're going to nerd out a little bit, people, so be prepared. So here's the what if question. What if we could develop sustainable pathways to convert molecules that we're breathing right now into the fuels and chemicals that we need for a high quality of life across the globe? That's the question. All kinds of opportunities for new tech. It needs to be affordable, needs to be sustainable, needs to be low carbon, needs to be reliable. That's the trick. And this is the multi-trillion-dollar opportunity. Many different molecular products out there, all of them with their own market. It's up to us to innovate on the technology space to make it happen. So just to give you a few figures of what the future may hold, these are two different plots coming from the US government. One's coming from the Department of Energy, one's coming from the State Department and from the Office of the President. They have somewhat different views to the future. Both of them are involving CO2 emissions across different sectors, as you can see. And there's a lot to digest in these plots as we look to the next decades ahead. But I think one of the key points that I want to make is that what they do have in common is that they agree that the electricity sector will be the easiest to decarbonize based on where we're at right now, but buildings and the industrial sectors are not. Those are the hardest. And so this is why it's such a terrific opportunity with all the forces coming into play for this energy transition. How can we come up with new opportunities to decarbonize these sectors, and in particular, into the industrial sector? Some of the things that we make in industry that are very high CO2 emitting: steel, cement, ammonia we talked about, plastics, aluminum. All of these have opportunities for making more renewable. The key here, and what we're going to be leveraging, is the dropping price of renewable electricity. To power these processes, you need energy from somewhere. 15 years ago, it's a non-starter. Price of electricity, way too high. But of course, it's been remarkable what we've seen in that industry. And so when we started our lab in 2007, we pretty much put a bet that electrons would be cheaper as time went on, and that bet is paying off. And so now with the mean price for unsubsidized wind and solar in the vicinity of 4 cents a kilowatt hour, that's opening up the aperture for using that electricity to power these processes to drive the chemical transformations we need to produce the molecules and materials that we need sustainably. So how do we create a new paradigm? Let's look at some numbers. The production cost for anything you'd want to make in dollars per kilogram, of course, is going to be a function of the CapEx and the OpEx. And the production cost for a lot of these things is around 50 cents to $1 per kilogram. That's pretty tough to catch up to. And so I would posit that these are the 4 numbers that if we were to hit technologically, we could reshape the globe. Renewable electricity, broadly at 1 cent a kilowatt hour. Carbon capture, $50 a ton CO2. Energy storage at $10 a kilowatt hour, because chances are you can't run a process intermittently or variably. We might need to store that electricity. And then you need to feed it into some box that we call an electrolyzer, where you feed in the water, you feed it in the CO2, you feed it in nitrogen, other feedstocks that we're breathing. And that box needs to be cheap enough, CapEx, such that it can take those inputs and make the molecules and materials that you need. So we could go through the techno-economic calculations together. I'm not going to dive into all the details, pardon me, I'm not going to dive into all the details, but just to let you know that that's how we think about it. We think about what's the market opportunity, what's the price that we need to hit, how do we go backwards on the techno-economics to figure out what should our targets be in the laboratory, that if we can hit those targets, we know we have a chance to scale that technology. That's how we think, that's how we work. So the idea is really we're trying to catalyze a sustainable future. That's the goal. The goal is to reinvent how we produce fuels, how we produce chemicals, how we produce plastics, how we make fertilizers, and how we can use renewables to the greatest extent possible to power these processes, not burning fossils to produce temperature and pressure, which as a chemical engineer myself, believe you me, I'm very fond of those processes. They're just not sustainable, they're not equitable. They have challenges ahead. So we need to come up with new options. That's the market opportunity. So our research group really focuses a lot on the catalysis at the atomic level, trying to develop catalysts that break bonds and make bonds just the way you want, and then we work on the devices, on the more applied side, trying to de-risk technologies so that we can get them out into the commercial space. I'm one of many at Stanford and SLAC that is contributing towards these research efforts. I serve as the director for a center called SUNCAT, the SUNCAT Center for Interface Science and Catalysis. We're a partnership between Stanford and SLAC. You can see some of my colleagues here. These are the senior personnel, many of whom are either rostered at SLAC or at Stanford or perhaps joint. And that's our superpower. You take all the resources and the intellectual firepower of a university like Stanford, as well as a national lab, and both are different types of organizations with complementary expertise, and we're woven together, we partner on everything. That's how we can advance these fields. We have computational folks, we have experimental folks, data science, AI, synchrotrons, free electron lasers, all kinds of cool things. So I'm gonna give you a couple of vignettes and then open it up to Q&A. The first one is on hydrogen. Hydrogen was brought up earlier. It's amazing what I've seen in the past just 2-3 years in terms of hydrogen. The number of announced projects on hydrogen is on the order of hundreds of gigawatts of electrolyzers. Hundreds of gigawatts. That's on the scale of the entire United States electricity grid. That's how many electrolysis projects have been announced. Well over 100 of those have already been financed. 100 gigawatts have been financed. And so that's a huge opportunity. The question I would ask is, do we have the technologies today needed to scale green hydrogen cost effectively? I've got a one-word answer. Nope. No, we don't. We have enough to get started, but not enough to take it to where it needs to be. So that's what's one of the areas in which our research group really focuses. So the Department of Energy recently announced a series of Earth shots. It's kind of like the moon shot, the Apollo program. We need to get to the moon. The Department of Energy is saying, we need to achieve these targets in several very important areas involving energy and climate. One of them is hydrogen. So Secretary Granholm has said we need to get down to $1 for 1 kilogram of hydrogen within 1 decade. And we can do that today with fossil resources, with steam methane reforming. If you make your hydrogen from natural gas, you can get to $1 per kilogram, but there's no electrolysis project that can do that, no matter how cheap the electricity, no matter how cheap the device. So here's an example of a module from ThyssenKrupp, and it's about $4 to $5 a kilogram, cannot compete head-to-head against steam methane reforming. So we need innovation in this space. And again, we've done the techno-economics, we partner with companies that work in this space as well. And there are many levers to decrease the cost of that electrolyzer, one of which is getting rid of precious metal catalysts. Now, I warned you I was gonna nerd out, and this is probably the nerdiest slide I've got, so bear with me. How do you make a non-precious metal catalyst? How do you make a catalyst that's as good as platinum or as good as iridium without using precious metals? We look to biology for inspiration. Biology lives in a world and has scaled in a world that doesn't have a whole lot of those types of elements. It had to figure out how to do it with more abundant elements. So I introduced you to nitrogenase and hydrogenase. These are naturally occurring enzymes. They're very good at producing hydrogen. And these are some density functional theory calculations, quantum mechanical calculations, trying to understand atomistically how do these things work. That was about 20 years ago when that work was published. That inspired us to start thinking about that. And then we said biology is great, not so easy to scale. Can we come up with solid state materials that are more robust, that could scale? And that pointed us in the direction of molybdenum disulfide. Very intriguing material. I could speak all day about it. It's in all kinds of oil refineries around the globe. Very important catalyst that cleans gasoline and diesel for lower emissions. It's also a lubricant. You could go to the hardware store and it works kind of like graphite. So when I started studying this, we started making nanoparticles of the stuff, and then nanowires of the stuff, and then nanoporous materials of the stuff, and then these small molecular clusters. On the top right, you're looking at atoms. That is a cluster of 16 atoms, 3 of which are molybdenum, 13 of which are sulfur. We can actually image these things, figure out what makes them work. And then we said, okay, these things are active catalysts. We were inspired by biology. We saw that there was sulfur, which was an important part of those enzymes. We started making molybdenum sulfides, which captured some of that. Cool, non-precious metal alternative to platinum. How does it work in a real device? And so we started, off of this knowledge, we started building all kinds of cool materials that are non-precious metal. And here's Mackenzie and Lori, who started scaling up some of our catalysts, shipping it off to Connecticut. There's a company called Proton Onsite that was acquired a few years ago by Nel, the Norwegian electrolysis company. They build commercial electrolyzers. In fact, they are staring at a commercial electrolyzer, but they sell it with platinum and iridium. And so Mackenzie and Lori made the non-precious metal alternative. We shipped it there, and it worked. So we have actually a viable option that could potentially replace platinum. So that's just one of many, many levers that we need to make these types of technologies more cost-effective and more scalable. Now, we've been doing the same thing with CO2. So water electrolysis, you feed in water, you make hydrogen, you make oxygen. Hydrogen already has a market of 70 billion kilograms a year. Carbon is way bigger. That's on the order of trillions of kilograms a year. Can we take air that we're breathing, which is 400 parts per million, as we said, of CO2, and feed it into an electrolyzer with water, ask our catalyst to break bonds and make bonds to turn that CO2 into something more valuable? And this is what Kendra, Natasha, and David had done early on in the lab, making all kinds of big ticket molecules, very important in our world. Methanol, ethanol, acetate, propanol, ethylene glycol, propionaldehyde, acetone. We can do all this at room temperature and pressure. It's basically like taking a bottle of Perrier or San Pellegrino, CO2 and water, pump electricity through it. These are the products that you can make. Now, there's more than just doing the chemistry. I want to share with you just one example. There's a lot of electrochemical processes happening in our world. We know batteries are electrochemical, redox flow batteries, water electrolysis for hydrogen, there's many. So we don't want to just work at the atomistic level. We want to figure out how devices work. And here's some work from Sheldon and Sangwan and Daniel in the lab, where they're building these electrochemical reactors, slicing them in half effectively and trying to visualize important processes. So I'll just show you one example of their work where, for instance, we can actually watch with optical microscopy under real-time operating conditions. We can watch, for instance, flooding happening and salt formation happening inside the devices. So this is more of a device-level work that when you're feeding in carbon dioxide and water, all kinds of interesting things are happening, not just in terms of bond breaking and bond making, but we can visualize processes that may or may not be helpful for your technology to scale. So we have different types of techniques, different types of studies at different scales so that we can try to make this thing into commercial tech ultimately. And so here's just some examples of some of the startups that have come out. These are former students and postdocs from the lab. On the top left, we see Kendra and Natasha that I mentioned earlier founded a company called 12. They're in Emeryville. They make CO2 electrolyzers. A company called Nitricity. They're out in the Central Valley. They have a farm. They grow tomatoes off of the air that they're breathing out there and turn it into ammonia fertilizer, electrified. There's Bill Chen, who has an electrified process to make hydrogen peroxide. Turned out to be a pretty important molecule as a disinfectant over the past few years, making it sustainably. And a more recent company, Dioxical, on carbon dioxide conversion as well. There are other companies, but just to show you that that's our goal, is to try to get the fundamentals so robustly and de-risked that we can then launch companies with them. The last point I'll make is part of the Stanford Doerr School of Sustainability. We have an accelerator that we've been building, which is designed to really accelerate these types of fundamental studies to get them de-risked down the line. So it's not just our lab, but many other labs can partake and launch just that many more companies that could be disruptive in the fuels and chemicals industry, in addition to many, many other industries that are relevant to sustainability. So with that, I want to thank my research team for all the work that you just saw today. Thank many different funding agencies coming from the federal government as well as from industry on some of the projects that you saw today. And would love to have discussions and partner with those who are interested in working together with us in the future. That's my contact information. Happy to take any questions for the time that we have. Thank you so much.
Okay, so I love your talk, and my main question is that how do you motivate the companies to do such things? Like, it's good to be like having a social cause and all, but do you see any ROI in all these type of things?
It's making money.
Yeah.
It's all about making money. It's all about being profitable.
Like if somebody has already invested in some type of energy, how do you motivate them to switch to this type of alternate source of energy?
You know, I do not have to motivate them at all, and that's the best part. I think I would say to a person, everyone I showed on that slide joined the lab not to become an entrepreneur, but to understand and work towards solving problems at the fundamental level. And during the course of their studies, as they're working towards their PhD, they realized that they were understanding things well enough to start thinking about what technology might look like that could make use of that innovation at that basic science level. And I think being part of this ecosystem of Silicon Valley and Stanford and SLAC and entrepreneurship, I think that kind of ecosystem really led them to think, maybe that's for me, even though they didn't come in necessarily with that as what they had in mind. It doesn't hurt also to have a graduate school of business on campus as well, where you have a lot of people who are very interested on the business side, but maybe not as knowledgeable on the tech side. And so that turns out to be a really important, it's a really nice environment, I'd say, for students to get together, and 12 is a great example of that. I mentioned Kendra and Natasha, as they were former students in my lab, but they connected with Nicholas Flanders from the Graduate School of Business, and that's how they launched their company.
Very nice presentation, and you covered quite a lot in such a short time. My question is that we need private sector, public sector, and academia to collaborate together to make the impact. And before you, two top-tier VCs were talking about that. And none of the private sector doesn't talk about the high-level mechanism, the government support, the $3 per kg for hydrogen that will make many of the current processes that are not commercially viable. And I see that your answer was no, but that sector continues to intrigue me. So if you can go a little bit deeper and say where you will see the innovation coming up in terms of the fundamental problem about electrolyzer, they cannot stop, the issue about storage, and scalability, reliability. If you can point out which sector I should look at for doing something or forming something, what would be your take on that?
Yeah, that's a great question. I think the short answer is that most of the chemical process today, and I say most, I mean like 99% of them, are driven by temperature and pressure. And that is a wonderful way to drive a chemical reaction. It makes all the sense in the world thermodynamically, kinetically, and from a scalable technology for centralized facilities. Now, if you say, I want to be more equitable and have greater deployment to other parts of the world, decentralization turns out to be a pretty good idea. It doesn't work so well for temperature and pressure. And when you say, oh, renewable electricity has dropped in price by a factor of 10 or 20 in the last decade, then that also changes the thinking. And the ultimate challenge is that I feel like those are areas, the electrified processes are not ones where those academic disciplines have not trained a workforce to the extent that we have a workforce trained in the other more conventional types of chemical processes. And so the ExxonMobils and the Chevrons and the Total Energies of the world, they're amazing at what they do at extracting resources and doing the chemical conversions. But that's not the same workforce that has been trained for these types of technologies. And so that's what we're trying to create, not only the new ideas on the new commercial opportunities, new types of tech, but also how do we create a new workforce that is well educated in that, because it's entirely wide open for innovation. Thank you.
Thank you.